Hi, welcome back. So today we will see about the potential due to system of charges and then regarding equipotential surfaces, and after that relation between electric field and the potential. So let's go. Potential due to system of charges. Here you need to consider different point charges which is located at a distance of say R1, R2, R3 and so on from the point P. So how will I write? Consider this as the origin. Instead of origin, let us take it as point P and say that this is Q1 at a distance of R1P, Q2 at a distance of R2P, similarly Q3, R3P, Q4, R4P. Like that you can consider number of charges. Q5 may be here. So now for the first charge Q1, if you consider one charge Q1 at a distance of R1P, then the potential V1 will be equal to 1 by 4 pi epsilon naught Q1 divided by R1P. Now for the second one, so what has to be done is, if we consider system of charges, then according to the superposition principle, we need to add the individual potentials. So in the same way, V2 can be written as 1 by 4 pi epsilon naught Q2 by R2P. Similarly for R3, it is Q3 by R3P, Q4 by R4P and like that. So when we consider the system, or in order to find out the total potential, we just have to add it. So V will be equal to V1 plus V2 so on up to Vn. V1 plus V2, if I consider n number of charges up to Vn. So it will be 1 by 4 pi epsilon naught will be common. Q1 by R1P plus Q2 by R2P plus so on up to Qn divided by Rnp. So this will be the total potential. Now if we consider the continuous distribution of charges, this is the single charge if we take. In a whole system, if I consider continuous distribution, we have studied this in the previous chapter for the electric field due to different types, correct? Linear charge density, volume charge density, surface charge density, like that. So if I consider the continuous charge distribution, then let us consider the volume charge density or rho. In one volume, delta V, if I want to consider, rho will be equal to Q by delta V. So now what is the charge? Rho into delta V, correct? Sigma will be the surface charge density, rho is volume charge density. So Q is equal to rho into delta V. So that system you have to divide into smaller volumes, then consider the total charge in that particular volume, and actually we have to integrate it because we consider the continuous charge distribution. So integrate it, saying that delta V tending to 0, then we get the potential of that particular system as a whole. So this is how we calculate the different charge densities and then consider the total volume and then find out the potential. So in the electric field, when we consider for the equally distributed surface, spherical surface or the spherical shell, when we consider, the electric field inside is taken as 0. We took it as 0. And electric field outside, what did we consider? It is taken as the same or equidistant from that particular radius. Correct? So in the same way, when we write the potential, so inside the shell, inside the spherical shell, no need to do any amount of work because charge is 0. So if we consider it as 1 by 4 pi epsilon naught q by r, where r is the radius. So inside this spherical shell, if you consider this as the radius r, so it is the same amount what we have on the surface. Outside the spherical shell, the potential, if you want to consider, then V is equal to 1 by 4 pi epsilon naught q by r, small r, where r is greater than the radius. Q is the total charge present in that spherical shell and r is at any point outside the radius. So R is greater than the radius. So this is outside, this is inside, where inside is same as that on the surface of the spherical shell. So this is just a part of the system of charges, potential due to system of charges. So this is just a part. So first consider the single point charges, then consider the continuous charge distribution. In that we consider this as sub point. Okay. So next we will move on to the equipotential surfaces. What are equipotential surfaces? So this is important. This topic is important. Equipotential surface. So as the name says, the potential is equally distributed on the particular surface where we consider. That is known as equipotential surface. At any distance which is considered from one point, which is situated at equal distance, so in that region the potential remains the same. So for the point charge, or if I consider plus Q, how is the electric field? Electric field is in this direction, which is moving away. If it is minus, it was moving towards this charge. So here it is in this direction, like this, outside, moving away from the point charge. So for the same point charge, if I want to represent the potential surface or the equipotential surface, it will be like this, the concentric circles. It will be the concentric circles. So wherever you consider on this, if it is R1, if this is R2, so wherever you consider the distance R1, the potential remains the same here at this region. Or otherwise, if you want to consider two planes, this plane and this plane, if you want to tell which are the two equipotential surfaces, then here this is one plane, this is another plane. So the potential remains the same in these two surfaces. So these two surfaces are now called as the equipotential surface. Or in other words, you need not do any amount of work to move the charge from here to here or from here to here. Wherever you consider, you need not do any amount of work in order to take the charge through this circle. But from here to here, you need to do the charge, you need to do the work. So there is a potential difference. But in that region, if you consider, no need to do any amount of work. That is why it is known as equipotential surface. Now you place this diagram on this one. How will it look? It looks like this. So it will be like this. That means electric field lines are always normal to the equipotential surfaces. Electric field lines are always normal to the equipotential surface, because if we consider this way, it is normal here. Normal means 90 degree. This is 90 degree. So you need to prove that for the equipotential surfaces, electric field lines are always normal. If it is not normal, you have to prove that statement. So now if it is not normal, what will happen? Say that it will have two or more other directions. Then you have to resolve that component. You have studied in vectors. So you have to resolve that and then find out. So in that case, what will happen? If you resolve that one, then you need to do some amount of work. But here there is no need to do amount of work because it is equipotential surface. There is no need to do work at all in order to move the point charge or any charge on that surface. So which is not true according to the definition of the equipotential surface. So there is no need to do any amount of work. If you resolve it into components, any other components you have to do. But here there is no because of the equipotential surface. So that means to say that for the equipotential surface or equipotential surfaces are always normal to the electric field lines. It is one and the same. So this is already given in your textbook, NCERT book also. But it is very important, and note that electric field lines are always normal to the equipotential surfaces. So if we consider any electric field line along the x direction, positive x axis, if you consider this way, so the equipotential surfaces will be like this. Maybe along y axis or z axis. Okay, so the electric field lines will be here. Then everywhere you need to consider the same parallel x, y and z axis. So which is perpendicular to the positive x axis. For a dipole, you want to represent equipotential surface. This is important question. For a dipole, dipole means system of equal and opposite charges separated by a distance of 2a. So in that case, how is the equipotential surface? It will be like this. They will not cross over each other. So electric field lines or the equipotential surface. If you consider equal charges, if I consider plus q and also plus q, so the equipotential surfaces are like this. Okay. So this is for a dipole, this is for like charges. Important question maybe for MCQ. Represent, or for 1 mark also, represent the equipotential surface for a dipole or like charges. So next is relation between electric field and the potential. Important for 2 marks. A small derivation where we will write the relation between electric field and the potential. What is needed here is you have to consider the equipotential surface again. 2 surfaces A and B. Those 2 are equipotential surfaces, surface A and B, equipotential surface. You consider point P here, which is at a distance of delta L from this surface. That means it is like this. You consider a point P on this surface at a distance of delta L. So this distance is taken as delta L. And say that electric field E is in this direction from A to B. You have to calculate or find out the relation between electric field and the potential. So now say that this is at the potential of V. That means amount of work done to bring any charge to this surface is in terms of V. And say here it is V plus delta V. That means there is an increase of delta V potential from A to B. If you want to move the charge from this point P to here, that means from the surface A to the surface B to surface A, then you have to do some amount of work because there is a change in the potential. So that work done, as we have studied, work done is nothing but force into displacement. Here force is considered as what? Electric field. So E into magnitude we will consider E into delta L. Delta L is the distance. So in order to move from here to here, that means you are moving against the direction of electric field. So this will be equal to VA minus VB. This work done is equal to the change in the potential between the surfaces A and B. So we will get E dot delta L is equal to V minus delta L. Sorry, V plus delta V. V plus delta V. So this E will be equal to minus delta V divided by delta L. This is the relation between electric field and the potential. It is minus because we are doing work against the electric field. This you can also write it as plus magnitude of delta V divided by delta L. It is one and the same. This is the relation between electric field and the potential. So I can write this as E will be equal to either delta V minus delta V by delta L or delta V magnitude divided by delta L. This is the relation between electric field and the potential. So the electric field moves down according where the potential decreases very steeply. So that is one of the statement that you can give from this equation. So we have considered A is at the lower potential, B is at the higher potential. So the electric field or the potential decreases accordingly. Okay. So this is a relation between electric field and the potential. And next is potential energy of a system of charges. And last topic we have seen potential of system of charges. Now it is potential energy of system of charges. A simple one, no derivation as such. Again here you consider any point charge Q1 or Q2 which is kept at a distance of say R1 or R2 from a point P. So that means first there are no charges in the system. You are bringing the charge from infinity to that point. So you need not do any amount of work or there is no potential there. So no need to do any amount of work. If there is already a charge and then you are bringing the second charge into picture, then you have to do some amount of work. That is stored as the potential energy. So now if I bring the charge, say you have two charges Q1 and Q2 which are at a distance of R1 and R2 respectively, then say that what will be V1 as 1 by 4 pi epsilon naught Q1 by R1. If there is a system already, there is a point charge already Q1, now you are bringing the charge Q2 in this region. Now what is the amount of work that you have to do? You have to do this much amount of work. So that means 1 by 4 pi epsilon naught Q1 Q2 by R2. R2 is located at R2 is the distance between Q1 and Q2. So first you need not do any amount of work. Second, if you are bringing, you have to do some amount of work because of the potential V1. Okay. So now this amount of work that is stored as potential energy U. That is represented as potential energy U. So now if we consider two systems or three systems Q1, Q2 and Q3. So now first if I consider two systems, this how can I write the distance as, so this potential energy is 1 by 4 pi epsilon naught Q1 Q2 by R12. R12 means distance between the charges Q1 and Q2. If I have three systems, if you bring Q3 into picture, say this is Q1, Q2, this is R12, this is R23, this is R13. Say that you have this system, 3 charges Q1, Q2 and Q3. First we have done for Q1 and Q2, now we bring Q3 here. So now what is the total potential? That is because of Q1 as well as Q2. So now V will be equal to 1 by 4 pi epsilon naught Q1 by R12 plus Q2 by R1. So you have 3 systems, Q1, Q2, and Q3. So it is Q1 by R1. I will consider it as P, the point P. Let me consider it as point P from any point, the first picture if you consider. R1P and R2P. For the Q2, let us consider it as R2P. Now bring Q3. So V will be equal to 1 by 4 pi epsilon naught Q1 Q3 divided by R13 plus Q2 Q3 divided by R23. This is the total potential. So Q3 will be here and R13 and R23. So you are bringing Q3 from Q1, it is at a distance of R13, from Q2 it is at a distance of R23. So first we will consider only P, any point P. Instead of origin, let us consider it as P. Now we will find out the total potential energy stored in that system. So it will be equal to, for this you have to bring one more, all the combinations that you have to do. So U is equal to 1 by 4 pi epsilon naught into Q1, Q2, Q3 divided by R13 plus Q2, Q3 divided by R23 and Q1, Q2 divided by R12. Q1, Q2 divided by R12. So this is the total potential energy of system of charges where we consider 3 charges. So it is a simple one. First consider the total potential, then amount of work done is what charge you are bringing into the total potential. So if you are bringing Q3, we have considered Q3 here, Q3 into the total potential, that will give you the potential energy of system of charges. I hope this is clear. First you have to write the equations clearly. Be clear with the equipotential surface. Before that, potential. What is potential? Say equipotential surface is where on the surface of that you need not do any amount of work because the potential remains the same throughout, which is at a constant distance from that point where you are considering. Then go with the relation between the electric field and the potential. There also you have to consider 2 equipotential surfaces. Calculate the work done when you have change in the potential from one surface to another surface. Then relate it with the electric field. Next is a potential energy. For this you have to consider the total potential and then calculate the work done when you bring one more charge on that potential. So that means that charge into the total potential will give you the potential energy of that system of charges what you are considering. Okay. Thank you for watching.